Welcome. In this series, we are going to deconstruct one of the most fascinating breakthroughs in modern AI, the diffusion model. At a high level, tools like DALL-E, Sora, or Stable Diffusion act as a translation engine. But instead of translating English to French, they translate language into visual reality. It starts here with a prompt. You describe a concept like a red cube. This is abstract, it's just a string of characters. We feed this description into the model. But how does a computer understand the idea of red or the geometry of a cube? Inside this box, a massive amount of computation happens. The model doesn't just look up an image, it calculates it, converting those words into a brand new, pixel-perfect visual representation. But to understand how it constructs this image from scratch, we need to look inside this box and understand the physics of noise. To understand how tools like DALL-E or Sora actually work, we need to step away from the complex neural networks for a moment and look at the core intuition. Let's imagine any image, a cat, a sunset, or a human face, simply as a structured collection of data points. Right now, these points have a relationship. The colors flow in a specific gradient. There is order. This represents the signal, the meaningful information we want the computer to learn. The training process for diffusion models begins with a surprising step: destruction. We systematically add random noise to the image, scattering its pixels until the original structure is completely obliterated. We turn the signal into static. In this state, the data has high entropy. To a human and to a standard computer program, the original image is gone forever. But here lies the breakthrough. If we can train an AI to observe this chaos and slightly predict where the pieces asterisk came from asterisk, we can reverse the process. Generation isn't about drawing pixels from thin air. It's about taking random noise and iteratively refining it, organizing the chaos back into a structured, meaningful image. This is the essence of diffusion, learning to restore a destroyed memory. To understand how AI creates, we first need to understand how it learns to destroy. This is the forward diffusion process. We start with a clean piece of data from our training set. Let's call this time step 0. It has clear structure and meaning. At each step forward, we add a small amount of Gaussian noise. Think of this like adding a layer of static over a television signal. At step 50, the image is grainy, but recognizable. As we continue this process hundreds of times, the noise accumulates. By step 500, the original information is struggling to survive against the randomness. Finally, at step 1000, the original image is completely obliterated. We are left with pure noise. Crucially, this transition from meaning to noise isn't random magic. It's a precise, mathematical path that the model memorizes. But if the model knows exactly how the image was destroyed, can it learn to play this movie in reverse? To understand how diffusion models destroy and create images, we first need to understand the mathematical recipe for noise. We don't just throw numbers around chaotically. We use a specific probability structure called the Gaussian, or normal, distribution. This bell curve is the engine of randomness. For our purposes, we use a standard normal distribution. It has a mean, represented by mu, of 0. This means that on average, the noise doesn't shift our image brighter or darker. It stays centered. And it has a variance, or sigma squared, of 1. This defines the spread, essentially how aggressive the static is. In AI research, you will often see this denoted as n of 0, 1. This is the standard setting for the noise added during the diffusion process. Now, let's visualize how this math affects data. Imagine this green sine wave represents the structured information in a clean image. To add noise, the model samples a random value from the bell curve above, most likely a small number near 0, but occasionally a large spike, and adds that value to the data point. When we do this for every point along the curve, the smooth structure is broken. The result is a noisy signal. The original information is still there, buried underneath, but it has been masked by the chaotic values drawn from our Gaussian distribution. So, how do we manage this noise mathematically? We don't do it all at once. We treat diffusion as a sequence of discrete time steps. Let's call our current image state math xt/math. In this process, the state of our image right now depends entirely on the state immediately preceding it, math xt1/math. This is a crucial simplification. And naturally, where we go next, to math xd plus 1/math, depends only on where we are right now. Mathematicians refer to this structure as a Markov chain. The key takeaway here is that the process is memoryless. To determine the next step, the model doesn't need to know the original prompt or where the noise started 50 steps ago. It only needs to know the current state to predict the next slight adjustment. This breaks a massive, complex problem into a series of tiny, manageable transitions.
Now, we face the fundamental challenge of generation. We've seen how easy it is to destroy an image with noise, but can we reverse it? On the left, we have pure, chaotic noise. On the right, a structured, clear image. The question driving modern AI is simple. Can we build a mathematical function that takes this random static and turns it back into that specific star? Mathematically, the answer is a hard no. Think about it. This pile of random pixels could have come from a star, a cat, or a landscape. The noise itself has lost all memory of its origin. It is an irreversible loss of information. To solve this, we can't just calculate the image back. We need a guide, a learned map, that understands what images are supposed to look like. This is where the neural network steps in.
Now, let's look inside the black box to understand exactly what the AI is doing at each step. At the heart of the process is the neural network, specifically a UNet in most diffusion models. But what does it actually calculate? The model receives two specific inputs. First, the image in its current noisy state, and second, the time step or T. This time step is a crucial hint. It tells the network exactly how much noise has been added up to this point. Without knowing when we are in the process, the model would be guessing blindly. The network takes these inputs and analyzes the pixels, looking for patterns amidst the chaos. Here is the critical part. The model does not try to output the clean image directly. Instead, it predicts the noise. It creates a noise map, essentially a guess of exactly what random pixels were added to the original image. By successfully predicting the noise, we can then mathematically subtract it from the noisy image to take one step back towards clarity. The AI is a noise hunter, not a painter. To understand how these models learn, we need to peek inside their training classroom. It starts with supervised learning. We take a clean source image, something we already have, and we deliberately corrupt it with known noise. Let's call this our ground truth noise. By combining them, we create a noisy input. Because we created this mess, we hold the answer key. Now, we feed only the noisy input into the AI model. The model doesn't get to see the clean image or the answer key. Here is the critical part. We ask it to predict. What noise is currently in this image? It outputs a predicted noise. To see how well it did, we compare its prediction against the actual noise we added at the start. We subtract the predicted noise from the actual noise. The mathematical difference between these two is what we call the loss. If the loss is high, the model adjusts its internal parameters, its weights, to minimize this difference. Building on the UNet architecture we just explored, the critical question becomes, how does the network actually learn to remove noise? It's not magic. It's a comparison game. Consider these two grids. On the left, we have the actual noise. This is the specific random noise we added to our image earlier. On the right is the predicted noise. This is what our UNet thinks the noise looks like based on its current training. Ideally, these grids should be identical, but notice the discrepancies. For any given pixel, the shade of gray might be darker or lighter in the prediction compared to the reality. This difference is the error. To quantify this error, we use a loss function, typically mean squared error or MSE. Mathematically, we take the pixel values of the actual noise, subtract the predicted noise, and square the result. This gives us a single number, a score, that tells us how far off the model is. Our goal is to drive this score to 0. We do this through gradient descent. Think of this arrow as a compass pointing downhill on the error landscape. It tells the network exactly how to tweak its internal parameters, its weights, to make the predictions slightly better next time. To perform this miraculous noise prediction, we need a neural network architecture that understands both the broad context of an image and its fine details. This is where the UNet comes in. Let's break down its shape, which gives it its name. On the left, we have the encoder. As the noisy image passes down through these layers, it undergoes downsampling. Ideally, we are compressing the image, throwing away pixel-perfect spatial information to gain a higher-level understanding of what represents the image, like recognizing shapes or textures. At the very bottom, we reach the bottleneck. Here, the image is compressed into its densest form, a latent representation. It's no longer pixels, it's a rich, abstract description of the image's content. Now, we need to turn that understanding back into a predicted noise map. This is the job of the decoder. It takes that compressed concept and performs upsampling, progressively enlarging the resolution back to the original image size. However, if we only used the bottleneck, we'd lose a lot of the fine crispness because we compressed everything so much. To solve this, UNet uses skip connections. Think of these as shortcuts. They copy detailed spatial information from the encoder directly to the decoder, bypassing the bottleneck. This allows the model to combine high-level context from the bottom with fine-grained details from the top. So, the data flows down to understand the context, across to preserve detail, and up to generate the prediction. With this architecture, the model can effectively look at a noisy mess and say, "I know this should be a sharp edge," and predict the noise accordingly. Building on the noise prediction concept, let's look inside the engine that makes it possible: the UNet. The architecture consists of two main arms. The first is the encoder, or the downsampling path. Imagine starting with a noisy image at a standard resolution, say 64 by 64 pixels. As we move down the arm, the model progressively shrinks the spatial grid, here to 32 squared, but simultaneously, it expands the number of channels. It trades spatial detail for semantic depth. By the time we reach the bottleneck at the bottom, the image is tiny, perhaps 16 by 16, but the stack of feature maps is deep, containing rich, abstract concepts about what the image represents. But we can't output a tiny abstract concept. We need pixels, so we enter the decoder arm. Here, we reverse the process. We upsample, stretching the grid back out, step by step, until we return to our original resolution. However, there's a major problem. Downsampling destroys fine details like sharp edges or specific textures. If we just upsample from the bottleneck, the result would be blurry and generic. This is where skip connections come in. These bridges act like a memory system. They copy the high-resolution details from the encoder and paste them directly onto the decoder layers. This gives the model the best of both worlds: the deep semantic understanding from the bottom and the crisp, fine-grained details from the top. Now, recall the UNet architecture we just saw. While the bottleneck at the bottom is brilliant for understanding concepts, it comes at a cost. As we compress the image down, we lose fine spatial resolution. We might remember there is a dog, but we lose the exact texture of its fur. To fix this, modern generators use what are called skip connections. Think of these as high-speed bridges connecting the encoder directly to the decoder. These connections allow fine-grained details to bypass the bottleneck entirely. They copy the high-resolution information from the start and paste it directly onto the reconstruction layers at the end. This ensures that while the AI dreams up new concepts, the final image remains crisp and sharp. With our architecture defined, let's look at the actual noise removal process. To understand how models like Stable Diffusion work so efficiently, we must first distinguish between two worlds: pixel space and latent space. Imagine attempting to paint an image pixel by pixel. In pixel space, a standard high-resolution image consists of millions of individual data points. Calculating relationships between all these pixels requires a massive amount of computational power. It is heavy, slow, and expensive. This is where latent space comes in. Instead of working with raw pixels, the model compresses the image into a much smaller representation. Through a process called encoding, we discard redundant pixel data while keeping the essential features or meaning of the image. Mathematically, The number of dimensions in latent space is tiny compared to pixel space. This allows the diffusion process to run on a manageable amount of data, making the generation of art not just possible, but fast. To make image generation efficient, modern AI models often don't work directly on pixels. Let's see why. This is our input image in pixel space, denoted as X. It consists of millions of values, a massive amount of data to process. To handle this, we use a component called a variational autoencoder, or V. First, the encoder takes this massive grid and compresses it, squeezing the information down into a much smaller, denser form. This is the latent space, or Z. Notice how much smaller it is. This compressed representation holds the essence of the image without all the heavy pixel data. This is where the actual diffusion process usually takes place. Once the AI has done its work here, we need to get the image back. So we pass this representation through a decoder. The decoder expands the compressed data, reconstructing it back into a full-resolution image, X hat. So, instead of calculating millions of pixels at every step, the model flows efficiently through this bottleneck, pixels to latents, latents to pixels. This is how we generate high-quality art without needing a supercomputer for every single image. Now, here is a critical distinction. Modern generators like Stable Diffusion don't perform this noisy work on the massive grid of raw pixels we just saw. Instead, they operate entirely within this compressed environment, what we call the latent space. Here sits our compressed representation. It is a dense mathematical summary of the image. During training, we systematically corrupt this data by adding noise, mathematically denoted as epsilon. We keep adding noise until the meaningful structure is completely destroyed, leaving us with pure, random static. But the magic of generation lies in reversing this. The AI model looks at the static, predicts the noise pattern, and subtracts it. Step by step, it peels away the chaos to reveal a clean, reconstructed latent pattern, ready to be turned back into a visible image. So, we've seen how the diffusion model can build an image from noise. But in modern generative AI, we don't just want any image, we want a specific one. We want control. Let's say you type the prompt, a blue cat. To you and me, this is a single meaningful sentence, but to the neural network, this raw text is just a string of characters. It can't digest the sentence whole. The very first step the model takes is to chop this input stream into bite-sized, manageable pieces. This process is called tokenization. The model maps each word, or sometimes parts of words, into its own discrete unit, or token. Suddenly, a continuous stream of language becomes a structured sequence of individual inputs. It sees the article A, the descriptor blue, and the object cat, all as distinct entities. This separation is crucial. It allows the model to later assign mathematical values to each piece independently, determining how blue relates to cat in a multidimensional space. But before we get to that math, we have to understand that for the AI, language starts as a list of separate tokens. So we have our text prompt, but here is the fundamental barrier. The diffusion model is a neural network. It doesn't speak English or French or Spanish. It only speaks math. To bridge this gap, the first step is tokenization. The model breaks your sentence down into discrete units or tokens, but these tokens are still just symbols. To the AI, they are meaningless labels. To give them meaning, we transform them into embeddings. This is where the magic happens. Each token is mapped to a specific high-dimensional vector, essentially, a long list of coordinates. Think of these numbers as coordinates in a vast conceptual space. The numbers for cat place it mathematically close to feline or pet, and far away from toaster or politics. These lists of numbers, these embeddings, are the actual mathematical instructions that will guide the noise removal process we're about to see. With our intent now translated into a language the machine understands, let's see how it uses this map to generate an image. To understand how a model like DALL-E or Sora creates visuals from words, we first need to understand how it thinks. Imagine the AI's brain not as a collection of images, but as a vast, multidimensional map, a mathematical space where every idea has a specific coordinate. Now, we have two completely different languages. On one side, we have human text, like the phrase "a cute cat." On the other, we have raw pixel data an actual image of a cat. To the computer, these look nothing alike. So, to bridge this gap, we use specialized neural networks called encoders. We have a text encoder to process the language and an image encoder to process the visuals. These encoders act as translators. They take these raw inputs and crunch the numbers, condensing the information into a mathematical vector. Here is the magic of a system like CLIP. The encoders are trained so that if the text and the image describe the same thing, they map to the exact same point in this space. Even though a cute cat is text and the picture is pixels, in this shared latent space, they arrive at the same destination. The AI now understands that these two distinct inputs represent the same shared concept. This mathematical alignment is the foundation of generation. Once the AI knows where a cute cat lives on the map, it can start generating pixels that fit that location. To understand how we control this process, we need to look at the inputs. We know this UNet structure is responsible for predicting and removing noise. But how does it know what image to reveal? How does it know a red car from a blue cat? It starts with your prompt. However, a neural network is a mathematical engine. It doesn't understand English grammar or vocabulary directly. So the first step is to translate your text into a language the model speaks. This list of numbers is called a text embedding. It captures the semantic meaning of your request, the redness and the carness, in a dense numerical vector. Now, look back at the UNet. Distributed throughout its layers are special gateways known as cross-attention blocks. Think of these as listening stations. We literally inject the text embeddings into these blocks. Through a mechanism called cross-attention, the UNet uses this text data to focus, or attend, to specific features while it processes the image. It's effectively telling the noise predictor, keep the shapes that look like a car and discard the ones that don't. This is how the text conditions the visual generation, guiding the noise removal process step by step towards your desired result. Inside the model, this connection happens through a mechanism called cross-attention. Think of the noisy image features as a query queue, asking questions. And think of the text prompt as a set of keys K, holding the labels. The model compares the image's query against the text's keys. It performs a dot product to create an attention map. This map tells us, for this specific pixel, which word is most relevant. If the pixel looks like a furry ear, it creates a high match score with the text token for cat. But we don't just want a score, we want actual visual information. This is where the values V come in. The values contain the rich feature data associated with the text. Using the attention map as a guide, the model pulls the specific values it needs from the text, blending them into the image to refine it. Mathematically, this is the famous attention equation. The queries look at the keys to determine how much of the values to let through. This is how a simple text prompt physically steers the pixels towards the final image. To understand how the AI knows asterisk where asterisk to place the object, we need to look at a mechanism called cross-attention. Let's visualize the image as a grid of patches on the left and our text prompt, a blue background, on the right. The model breaks down your prompt into individual tokens and calculates how much each pixel on the canvas should pay attention to each word. Take the word blue. The model associates this concept with the subject of the image. Through training, it learns that subjects are often central. So, it casts a strong attention score from the word blue to the pixels in the center of our grid. Effectively, it is painting a semantic heat map, telling the generator, put the blue features here. But the model also needs to handle the rest of the image. It looks at the token background. It maps this concept to the surrounding areas, activating the pixels at the edges. It tells the noise predictor that these areas should look like the environment, not the object. This resulting pattern is what we call a cross-attention map. It acts as a spatial blueprint, guiding the diffusion process to ensure that blue appears in the middle and the background stays, well, in the background. So, how do we actually use that UNet architecture to generate an image? We use a process called iterative refinement, often referred to as the sampling loop. Think of this as a cycle of gradual improvement. We start at the top with pure, random static, our initial state, xt, but this time, we don't just feed the noise into the UNet. We also inject our text prompt, for example, a cat. This text acts as a guide, conditioning the UNet to look specifically for cat-like patterns within that randomness. The UNet analyzes the noisy image and the text, and it makes a prediction. Here is the noise I think needs to be removed to make this look more like a cat. We take that predicted noise and mathematically subtract a small fraction of it from our image. We aren't done yet, though. We check our time step counter T. If we haven't reached 0, we loop back to the start. But notice, the image at the top is now slightly less noisy than before. We repeat this cycle dozens of times. Predict noise, subtract, repeat. With every single loop, the chaos recedes and the structure of our prompt, the cat, emerges from the static. Finally, when the counter hits 0, the noise is gone. The loop breaks and we are left with our final, clean-generated image. Following the noise prediction, we arrive at a critical component known as the scheduler. To understand this, let's visualize the denoising process as a graph. On the left, at t equals 1000, we have pure noise. On the right, at t equals 0, we have our final, clean image. The model follows a specific curve, or schedule, which dictates exactly how much noise should remain at each stage of the generation. This curve is the map from chaos to clarity. Ideally, we want to move down this curve very carefully. We take a small step, subtract a tiny bit of noise, recalculate, and take another small step. This creates a very high-quality output because the model never makes a drastic, uneducated guess. It's like sculpting a statue by sanding it down grain by grain. But there is a catch. This approach requires calculating the neural network hundreds or thousands of times. It is incredibly slow. So, modern schedulers use clever mathematics to take shortcuts. Instead of baby steps, the scheduler allows the model to take giant leaps down the curve, skipping from step 1000 directly to step 900 or 800. It predicts what the image would look like if we had taken all the small steps in between. This allows tools like DALL-E or Stable Diffusion to generate an image in just 20 or 30 steps instead of 1,000, making the magic happen in seconds rather than minutes. Creating a high-quality image requires a clever trick called classifier-free guidance. You likely know this as the CFG scale or guidance scale slider in your interface. To understand what that slider does, let's visualize the model's decision-making in latent space. At every single step of the diffusion process, the model actually makes two simultaneous predictions. First, the unconditional prediction, shown here in gray. This is what the model wants to draw based on general patterns, ignoring your text. Second, the conditional prediction, in blue. This is what the model draws when it tries to follow your text prompt. Now, you might think we just use the blue arrow, but often that's not strong enough. So we use this formula. We calculate the difference between the prompt's path and the generic path. This dashed line represents the pure essence of your prompt, with all the generic stuff subtracted out. This is where your guidance scale slider comes in, represented here by S. We take that difference vector and multiply it, essentially turning up the volume on the prompt's influence. Note how we push strictly away from the generic gray arrow. The final step, shown in red, is the vector sum. By adding this amplified difference back to the start, we get a new direction that adheres to your text much more strongly than the model could have achieved on its own. This is why high guidance values make images follow prompts closely, but can burn the image if pushed too far. The vector pushes too deep into extremes. Building on the denoising process we just finished, we have arrived at a crucial milestone. We now possess a clean latent. Notice how small and dense this grid is. This is a highly compressed mathematical representation of our image, pure structure, but no visible pixels yet. Humans can't see this. To turn this math back into art, we need one final component, the VAE decoder. Notice its shape. It acts as a bridge, designed to translate and expand compressed data. Think of this step like unzipping a massive file or developing a film negative. The decoder takes the concentrated features from the latent space and projects them outwards, interpreting the semantic information to reconstruct the millions of individual pixels that make up our final, high-resolution image. In formal terms, we describe this as x equals d of z. The decoder, d, takes the latent, z, and maps it back to the pixel space, x. The journey from text prompt to visual reality is now complete. So far, we've visualized diffusion as a process happening on a static image. We can think of this image as a simple flat grid defined by just two spatial dimensions, height and width. But modern video generation models, like Sora, need to handle motion. To do this, they don't just generate one frame at a time. Instead, imagine taking that single 2D frame and extruding it backwards, creating a new axis. In this 3D structure, this depth dimension represents time. We call this a space-time volume. A video isn't seen as a sequence of separate pictures, but as one solid block of data. Mathematically, this means a pixel's value is no longer just a function of x and y. It is now a function of x, y, and t. By treating video as a volume, the model ensures consistency. However, processing this entire volume at once is computationally expensive. So the model breaks this volume down into smaller, manageable 3D chunks called spacetime patches. Let's see how that works. Building on the image patches we just saw, let's step up a dimension to understand how models like Sora handle video. Instead of seeing video as just a flat sequence of images one after another, these models view a clip as a single, solid, three-dimensional volume. Here, we have the standard height and width, but time becomes our third spatial dimension. The video is effectively a block of spacetime. To digest this massive block, the model slices the entire volume into smaller, cubic units. These aren't just 2D squares anymore. They capture visual information and temporal motions simultaneously. We call one of these distinct cubes a spacetime patch. By isolating this patch, the model captures not just what is happening in a specific spot, but how that spot changes over a brief moment in time. Finally, just like with text or images, this 3D patch is flattened and projected mathematically into a single sequence, or token. This is the key. Once it becomes a token, the AI treats it exactly like a word in a sentence, allowing it to learn the complex physics of our world using the same architecture that writes poetry. Building on our understanding of static images, let's enter the fourth dimension, time. In video generation, we aren't just painting a single canvas. We are generating a sequence of frames that must flow logically. Imagine we are currently generating the pixel at this specific location in the latest frame, time t4. If the model generates this pixel in isolation, it might pick a random color. Do that for every frame, and your video will flicker uncontrollably. To solve this, models use temporal attention. The model literally looks back through the timeline. It attends to the features at the same spatial coordinate across previous frames, creating a temporal link. This allows information to flow from the past to the present, ensuring that a blue sky remains blue and a moving object maintains its identity, frame after frame. Building on our understanding of tokens, let's see how this applies to world simulation. Consider a ball thrown through the air. In traditional programming or video games, we would explicitly code the laws of physics, telling the computer exactly how gravity affects the ball's position over time. But generative video models, like Sora, don't have these equations inside them. Instead, they look at the video as a sequence of visual patches. The model analyzes these initial frames, the context, and asks a simple question. Based on these pixels, where should the patch go next? It doesn't calculate velocity or acceleration. It simply predicts the most probable next patch that continues the visual pattern it learned from watching millions of videos. When this process repeats frame after frame, a physically accurate trajectory emerges. The model has essentially learned gravity, not by studying Newton, but by observing the world. Let's zoom out and look at the entire architecture we've built, summarizing the journey from words to pixels. It all begins with your text prompt. This text is fed into the text encoder, like CLIP or T5. The encoder translates your words into embeddings, a mathematical representation of your concept. Separately, we start with a canvas of pure random noise. The UNet takes both, the noise as its raw material and the text embeddings as its blueprint. It enters a loop. Step by step, the UNet predicts the noise and subtracts it, guided by your text, gradually revealing structure within the latent space. Once the noise is fully refined, this compressed data is sent to the VAE decoder. The decoder expands the latent information back into pixel space, generating the final, high-resolution image. And that is the complete pipeline. From a simple thought, interpreted by language models, processed by diffusion, and decoded into a visual reality.